So, our first keynote speaker is Jawad Ahmed, who is a staff applied scientist at Loblaw Digital, supporting different ML teams building personalization and recommendation system in Loblaw's digital products for different line of businesses of Loblaw Companies. Jawad completed his master's from University of Waterloo in Ontario in computer engineering focused on artificial intelligence and machine learning. He has 8 years of industry experience in applied AI in the domains of speech recognition, NLP, and recommendation systems. Prior to joining Loblaw Digital, Jawad worked at Flipp, Dialpad, and McKinsey Solutions in the applied science and data science teams. So, with me, welcome, Jawad.
Okay, thank you. My name is Jawad. I work as a staff applied scientist at Loblaw Digital. The topic for today's talk would be just covering different machine learning use cases we have at Loblaws and Loblaw Digital. So yeah, just the agenda for today's talk would be covering different lines of businesses within Loblaw Digital, different machine learning teams we have, uh, and the different problems being solved across different teams, and some of the underlying algorithms. So I'll just try to touch different use cases of MLVC here. So prior to Loblaw Digital, I joined Loblaw in June last year, and I worked at Flipp previously as a senior data scientist. And prior to that, I was at TalkIQ, which was later acquired by Dialpad. And there I worked on speech recognition, natural language processing, on conversational data. So it was conversational AI. And prior to that, I was at Affinity, which works in call center pairing optimization of agents and callers. Rather than FIFO-based routing, we do intelligent routing. That's my background. And coming to Loblaw. So Loblaw Digital is the digital wing of all the digital properties of Loblaw. Uh, as you'd know, like Loblaw companies operate multiple banners like Shoppers Drug Mart, Real Canadian Superstore, AT&T, No Frills, and multiple ones. So in healthcare and in personal finances, in grocery, in marketplace as well. And since 2020 onwards, so this business has grown significantly, resulting in more than $2 billion in sales from the digital platforms only. Okay, and just some data points on the number of users and the different banners we have. So within Loblaw Digital, now the colleagues are close to 700 and have multiple apps, websites, and for each banner, there's a separate website. But within the app, they can capture all those. So just highlighting different areas. Okay, so just now looking at an e-commerce platform from a data perspective, just want to break it down how we look at it currently. So in any e-commerce shopping platform, we have users' data, which could be users' identifiers and any metadata around users, demographics, or any other things. And then we have content data, which is the content which is on the shopping platform, which has product catalog, has the inventory information, has the textual descriptions of products, images, uh, categorization taxonomies within that business. And then we have user to item transactional data, which is the sales transactions data, whether those sales happen in person or through the app. And then user to item interaction data from the websites and these apps. And from the line of business point of view, on the right side, we divide it into these four main pillars. We have PC Express, which is an app. You can use it to deliver grocery or to pick up grocery, and you can find all the banners from No Frills to Real Canadian Superstore, Loblaw, Zahir's, but they all cater for the grocery products for which the shelf life is smaller and freshness is ensured and stuff like that. So that's PC Express. And then we have Shoppers Drug Mart, which deals with the products sold in Shoppers Drug Mart, and pharmacy is a component of it. And then we have GeoFresh, which is clothing and apparel business. And also then we have marketplace now, which you can see on PC Express, where there are individual sellers, approved sellers. There's a third pillar also, which I would like to, it is called retail media platform. So we also serve ads in different places in our websites or digital landscape. And so that's retail media platform. So for that, you can think of it as an ads business as well from the CPG partners. And now coming to the machine learning use cases, I'll just, all the points which I mentioned here, I'll just try to highlight different areas from the app. And so personalized carousels is one use case of machine learning. Uh, in on any website, in our websites, there's a home page and then there's a product page. On home page, there are carousels like, sorry, recently viewed, um, you may also like, so that's based on your past transactional history. So specialized recommended for you kind of carousels are personalized carousels to the catered to the user, which are using recommendation models underneath. Customers also viewed in Shoppers Drug Mart. That's another example. It's like using collaborative filtering, uh, or other approaches too. And then on the product pages, PDP product pages, where we have a product page, we have similar items underneath it, like carousel or related items, or so that's an item to item relationship, agnostic of the user. And then we also have complementary products. So if someone's buying a hot dog, we can recommend them a bun, things like this. So what are the good complements? So all of these applications have machine learning use cases behind them for each line of business, for each different use case of the carousel. Okay. And then this is just an example of GeoFresh. We internally we trained a model using self-supervised learning, contrastive learning. It's a network called SimClear, where by contrastive learning you can learn image similarity in a self-supervised manner. So here you can see, like, given this image, these are the most visually similar images. Now in fashion and apparel, visual similarity matters much more, what we observed, than for example in grocery products. In those cases, the textual data has the main gist of the product information, whereas in these some of these fashion products, the majority of the texture, the color, the pattern is captured in the image. So this is an example of, we can make a carousel out of it, which is similar products carousel. So when a user is on this when a user is on this product page, they will have this carousel. Yeah, so this model, just to give you an idea of, so we have this visual similarity dashboard. I just activated it for this presentation. So you can pass in any product from any brand. So this is not a Joe Fresh product. Took an image from the internet and just drag it, and it will return you the top 5 visually similar neighbors from the catalog of GeoFresh. And you can imagine the use cases we can have within that for similar products. So this is the model which is serving similar products in our plans. So that's another use case, visual similarity. Then in product substitutions, so product substitutions are products which can be substituted, but they serve the same purpose. We have a full 40 minutes, or yeah, full talk, I think 35 minutes talk in TMLS on just specifically this topic of product substitutions and how we solve them. So as in, like, if you shop something and at the end, the product is in low stock or out of inventory, we give you options of choosing some substitute products. And this is a way we can collect this data over time as well, using active learning. And we also have ground truth data to see what's actually a substitute and what's not. So the use case there is only for PCX products. A simplified version of this product substitution model is that we take the text representations and the image representations, and then we combine them with certain weights to have the final ranking of a product similarity against a given product. So we are taking both the textual and image similarity features, not similarity, textual and image representations, and using them to finally compute similarities. Uh, so to that, to do text modeling, we have done mass language modeling uh, from the very scratch, as in that we are not attaching an MLM head on a transformer to fine tune it, but rather we pre-train a tokenizer first, a BPE tokenizer on our own corpus. So the tokenizing, I'm not sure if people have used transformers or so there's a component of tokenizer, which is also a trained process. So we train tokenizer on our own corpus so that the word splits are based on how our corpus looks like. So these are, and then the mass language modeling task is to, we dynamically mask 30% of the tokens in the representations, and then allow the model to do this mass language modeling task. And once that encoder is trained, and also it's a custom model, which means it's the number of encoder layers, the transformer dimensions are chosen dimensions. Like they're not Roberta specific, but they are Roberta architecture based. And we can see that we trained this model on mass language modeling. And here on the label side, we just attached some different categories. We haven't trained the model on category classification task. And we can see that the embedding representations from textual representations are very well formed, that they're capturing the similar group of products together. So qualitatively, to look at that, these are some of the PCX examples. PCX means PC Express. So given this product, these are the top similar products which came out given the leftmost product. We are looking at the images, but the underlying similarities based on the textual description, where we are using name, brand, some categorical information, unit of measurement, and also modeling it in our own way. TMLS talk has all those details. But these are the qualitative results from the mass language modeling. And then on the image front, we use this. There's a paper by Professor Geoffrey Hinton, Sinclair. So we use it with the backbone model of currently ResNet 18, but it can be anything, ResNet 50 or even Inception or any visual encoder. And then using this framework and a certain loss function, we can train an image similarity kind of encoder without having explicit labels. In that case, designing good image augmentations is important, but so these are the results from just image-based similarity. And we can notice that visually, some of these products look similar, but they would be very different. For example, like this third product and this second product is very different, but if I just squint my eyes, visually they look similar. But in this case, we see that in grocery products, visual similarity shouldn't take a higher weightage. Rather, text similarity should. Okay, and then another use case is personalized search. Personalized search it has different components to it: query completion, query suggestion, and then once we have the query, then query parsing, whether if there was a brand in the query, or we're also looking at query understanding from having vector representations for queries, now that we have product representations as well. And then once a user has selected a query and the products have to be retrieved, there's a learning to rank model, which is a personalized approach in this way, that for logged in users, the ranking is personalized, taking into account the recommender systems. This second part in the picture, where the ranking of products which you can tie could vary, just as an example. Okay, and on the recommender systems, that's a whole different, there's a full team for recommender systems, and the use cases are different. So whenever I use the term recommender system, it's a personalized recommendation system. So it's powering search, personalized carousels like recommended for you types, content recommendations. We can even use it to design the home landing page differently for each user because we have a way to compute user to item affinities. Uh, Product placements, email recommendations. So these are all different multiple use cases of recommender systems. And the bigger high level architecture of recommender system, which we have at Loblaw, it's an evolved form now, is we've named it Universal Encoder Recommender System. So it is based off of an approach, a collaborative filtering approach on the one hand, where we are using NCPL rec. And then here, these where you see from TLog, these embeddings come from NCPL rec. So the transactional data results in item embeddings and user embeddings. Then apart from that, we have user features, and then we have ways to encode the content like the product data as well into the model. So now this recommender system doesn't only work on transactional data, but it has transactional based representations, transactional data based representations, and then content representations, user representations, and then it gets trained later on using those representations as features. And the good thing is the target can be anything, click-through rate, for the users for which who are not logged in. If we want to maximize margin, then we can tune our recommender system for margin. And that's the idea of just we started with NCPL rec or BPR prior to that, which is collaborative filtering based approaches. NCPL rec is still being used in this architecture, as in it provides that transactional embeddings, transactional data embeddings. Okay. There's sorry, I didn't mention it, but we have 4 ML teams currently, which so one ML team is personalization team. These are the teams which are producing multiple carousels for different lines of businesses, training these image similarity models, and so that's personalization team. Then there is a user content modeling team who make these UERS models, recommender systems architecture. So they build tools to be used by other teams too. And then there's another third team, which is the search team. So they work on search across all lines of businesses. There's another team which is ops and forecasting team. So the skill set of this team is a little different in this way that we have expertise here in operations research and optimization problems rather than machine learning. And the projects they work on are the actual physical, say, for physical stores, demand forecasting, sales forecasting for different items, and then with the app usage, as you see, like you can pick a delivery time or a pickup time, but the grocery products are like we have to ensure freshness, and people can choose 4 days from now to pick anything. So how do we ensure that on-shelf availability would be there when by the time when the user goes or when the picker starts making their cart? So these are really hard problems, I believe, because they actually involve implementing ML not on an app but on the actual physical level. So we have a team in that. Yeah, so just some of the underlying algorithms, just to since this is an ML platform. So we are using self-supervised learning algorithms like mass language modeling with our custom tokenizer processing, and we're using Roberta architecture for now. Contrastive learning for visual representations, like SimClear is an example. We plan to explore Clip as well this year, which is combined image and text representations. Transformers, pre-training, fine-tuning, and then for large-scale similarity search, we are also using FAS, which is like vector search by Facebook. Recommender systems, as I shared, like previously we had NCPL rec, and now we have UERS, and these are huge architectures in the way that they're serving multiple downstream tasks, and as you can imagine, the user base is huge. So that's important things. Yeah, just that's all from my side. Thank you.
Thank you, Jawad. That was really insightful presentation, I would say. I see some great questions for you here in the chat, but with the time limitations, we cannot take them right now. However, what we will do is we will copy this question and send it to you after the event so that you can answer them for us.
Good. Thank you.
Perfect. Again, thank you very much, Jawad, for your time.